ready to start solving general logarithmic equations. What I mean by that is these are more difficult than some that we looked at earlier. With these, we actually have to use some log properties or exponential equations. Okay, and we'll look at that. So first of all, let's get a strategy, kind of like what we did with exponential equations, to see if we can kind of figure out what's a good way to approach these things. And so the first thing you need to identify when you have a logarithmic equation is there a constant in the equation? Okay, if there is, you're going to have to exponentiate. And you may need to use properties of logarithms before you can actually do that. If there's not a constant in the equation, then what we're going to try to do is isolate one log on each side of the equation. And we might also need to use log properties in order to do that first. And there is one other thing we need to keep in mind. When you're working with logarithms, remember that the domain of a logarithm is only from 0 to infinity. So we're going to need to check our solutions to make sure that our solutions actually make sense. So keep that in mind. Now let's look at some examples and I'll try to explain this process. Now before we start these examples, it would also be good to review our properties of logarithms. So remember that with logarithms we have three key properties. The first one is if you have log base a of x plus log base of y, that's the same thing as log base a of x times y. So you can bring down, so the addition of two logarithms becomes the product of what's inside. Similarly, if you have subtraction, when you bring them together, you get division. You get x over y. So log base a of x minus log base a of y equals log base a of x divided by y. And the third property is if you have log base a of x to the n power, that exponent actually comes out in front as multiplication. And we saw that that property in particular is very useful when solving exponential equations. All right, so let's look at part A. So first of all, notice there is a constant on one side of this equation. So I know I'm going to have to exponentiate both sides. In other words, I'm going to raise both sides to some power. All right, now the first thing I want to do though is I get the log x plus log x minus 3 together as one logarithm using my properties. But remember, the addition of two logs is the same thing as multiplying what's inside. So this is the same thing as saying log x times x minus 3 equals 1. Okay, now remember, when I just write log by itself, that is understood to be log base 10. So what I can do is I can exponentiate both sides, or in other words, do my whirlwind property here. I can say 10 raised to the power of log x times x minus 3 equals 10 to the first power. And that looks confusing, but remember, since this is log base 10, 10 raised to the log base 10 of that power, they kind of cancel each other out. So we end up with simply x times x minus 3 equals 10 to the first power, which is 10. So in other words, all of this here reduces down to just being x times x minus 3. From here we just have looks like a quadratic equation. We solve and hopefully get a good answer from there. So we have x squared minus 3x. It's quadratic, so we need to get 0 on a side, so I bring over the 10. Now I try to think of two things to multiply to give me negative 10 and add to give me negative 3. How about minus 5 and plus 2? So I end up with answers x equals 5 and negative 2, and there we have it. Well, not exactly. We don't quite have it, because remember what I said, that the domain of the logarithm is 0 to infinity, 0 not even included. So if I have a negative value in my logarithms, it won't work. So if I plug in 5 here, I have log 5 plus log of 5 minus 3, which is 2. 5 works, okay? But if I plug in negative 2, I have log of negative 2. I know that's not going to work. And you can see here, negative 2 minus 3. That's not going to work either. So the negative 2 is actually not a real solution. So my only real solution here is x equals 5. This shows you the importance of checking your solutions, right? So we had a check there. All right, let's go on to part B. So we follow our flowchart. Does this have a constant on one side? No, it does not. Okay, so that means we need to try to get a log on each side. Here we do. And we don't even need to use properties of logarithms to take care of this. Notice that I have log base 2 on both sides. So since I have a common base, in other words, since I have log base 2 of something equals log base 2 of something, I know that what's inside has to be equal. So all I have to do is actually just drop the logarithms. So I end up with 7x minus 4 equals 16 minus 3x, which is a simple linear equation. Now what's really going on here, just like we did last time, what I'm technically doing is I'm saying 2 to this power equals 2 to this power, and just like last time, 2 to the log 2 power, they cancel each other out. So in other words, the net result is like I'm just dropping the logarithms, and we end up with this linear equation, okay? So this is probably about as easy as it can get in college algebra. I just add 3x to both sides, get 10x. Adding the 4 over, I get 20. And so I end up with x equals 2. And we do need to check our solutions, okay? So we're going to check here quickly. If I plug in 2 in for x here, that's 7 times 2 is 14 minus 4, so that's 10. I'm fine. If I plug in 2 here, I get 16 minus 6, that's 10. That's fine. And notice that they are the same thing, which is what we hope for. So that does work. 2 does check, and there's my solution. I'd like to go over a couple more just to show you more of this process. So let's just take a look. All right, now for part C here, we're going to have log base 5 of x minus 1 plus log base 5 of x plus 4 equals log base 5 of x minus 5. Okay, following our plan, is there a constant on one side? No, there's not. So I'm going to try to get a logarithm on each side. And I might have to use properties of logarithms first to do that, which I will here. But it's pretty straightforward, right? Because since I have plus, I know that this is going to bring together as what? The multiplication of what's inside. So I have log base 5 of x minus 1 times x plus 4, and that's equal to log base 5 of x minus 5. From that point, since I have log base 5 on both sides, I can simply just drop the logarithms part and end up with a quadratic equation. X minus 1 times x plus 4 equals x minus 5. Foiling this out, we get x squared plus 3x minus 4 equals x minus 5. And remember, the plus 3x comes from minus 1 times x and plus 4 times x, if you FOIL that out. And then I have x squared bringing everything over, plus 2x, negative 4 plus 5, right? It gives me a plus 1, gives me 0. And then this is going to factor two things to multiply to give you 1, add to give you 2. How about plus 1 and plus 1? So I end up with x plus 1 squared. So then here I end up with x equals negative 1 2 times. Now don't be afraid for it to be negative, because when I plug it in, it might work. But let's see, when we check, if I plug in negative 1 there, look, I get negative 1 minus 1. So we see that negative 1 doesn't check. So what happens here? That means that this situation has no solution. That means that no real number can make this equation a logically true statement. We're looking at a lie regardless of our value of x. Alright, I want to show you one more that I found interesting, and hopefully these are making sense. Okay, so here this time I have ln of 3e, and remember ln is log base e equals log x. Alright, so this one looks weird to us because we have two logarithms and they're different bases, right? And so we got to think, then going by our chart, the first thing, is there a constant on one side of the equation? And we say no. So then we move on to, is there a log on each side? And you might say yes. And that's actually incorrect, because remember that e is a number, right? So log base e of 3e is a constant. This is a constant here. So we do have a constant on one side, which means that we're going to exponentiate based off this logarithm. And since that's just log x, remember that's base 10. Okay, so I say 10 to raise to these powers. I'm going to end up with x on this side because I have 10 to the log x power. Those cancel out. Equals 10 to the ln 3e power. And 10 raised to the ln 3e power is a real number. This is our solution. If you plug this in a calculator carefully, you should get then that x is going to be approximately 125.49. Alright, so that should be what you get. Alright guys, I hope this makes sense. This process I showed you will solve almost all logarithmic equations that you'll encounter, especially in a college algebra class. If you need help with anything, I'll be glad to help. And thank you for watching.